I'm going to introduce you to Declan Coleman, who works over at Arup's office in Belfast. Declan claims to only have a few months' experience with FME, but I've had a sneak peek at one of his FME workspaces, and it's pretty clear actually that he's already embracing it. Declan's going to give us an overview of the topological analysis that he's done on Northern Ireland Water's utility data to ensure a road improvement scheme went to plan. So thank you, Declan.
Awesome. I just want to pre-apologize if there's any noise coming through because there is some development work going across from my apartment. So it's just if there's any banging going on in the background, that's what it is. So yeah, I'm just going to talk about some work that I've been doing with the water team at the Arup Belfast office, looking at trying to automate their decision process for developing drainage systems. And this was using the A2 as a case study. So yeah, just a little bit about myself. So I joined back in August of last year as a graduate analyst, and I work as part of the digital insight team. And as David mentioned already, it was basically my first time working with FME. Is when I joined Arup. Prior to that, I have had experience working with spatial data, but this was the main project that I got involved with, which actually kind of gave me a bit more insight into the capability of the software. So it was diving straight into the deep end, but it was definitely a very good opportunity. So we'll talk a bit about the background of the project here. So the A2 Buncranna Road improvement is a project based in Northern Ireland in Derry/Londonderry City. It's a 4.4 kilometer two-lane road that goes from the city centre out towards the Republic of Ireland, towards County Donegal. It's split by about three-quarters urban and a quarter rural. And the proposed expansion is to make it into a four-lane road slash dual carriageway. And based on this expansion, especially within the rural or so the urban area, the water team have been looking to try and incorporate new drainage systems to take in this new surface water that will be flowing around that area. And in order to do that, they settled on implementing some sustainable drainage systems. So namely, they looked at attenuation ponds, but the whole point of this is to transport the surface water based on the natural contours of the land and store it before it enters the watercourse. And this allows a lot of the water to percolate into the ground surrounding it or evaporate out or be used by the local vegetation. And the benefits of using a sod over a traditional drainage system is the fact that it actually boosts the local biodiversity, both in the water and on the surface as well as boosting actual local quality as well, water quality, sorry. So why deploy sods? So Arup take the Sustainable Development Goals very seriously. So as we can see here, deploying these sods actually allows us to reach 10 of these goals. And I mentioned there briefly about so life above water and below water and clean water and sanitation are some of the things that sods directly affects. So that's why it's quite important that we reach these goals. So this is where I come in. So I was approached by the water team to develop a reusable tool that they could use to assist them in the planning stage of sods development. So previously they were going through the catchment data and the surface flow network data manually on a neighborhood level and trying to identify main runs which they could potentially connect these attenuation ponds to. So they wanted something that they could run at a larger scale to help them identify on a city scale, for example, where they could place these ponds. So in order to do that, they needed to have the data visualized so that they could isolate the surface collection network, have the main runs isolated and symbolized so that they could find out where those runs were when they needed to connect the ponds up. And then the data, based on future processes, they wanted to comply with BIM protocols. So they needed every single run within the network to have a unique ID. And this was to be dictated based on the topology. So its position within the network itself, so that it could be updated based on changes in the network and future developments, which meant that every single time that this workbench was run again, that it would update to adjust to that new change in the topology. And there was also associated catchment data for this area that was taken from remote sensing data, I believe using Spectral Data. And this allowed them to produce so shapefiles that basically had attributes that showed both the potential volume for the catchment areas, but also their permeability rates as well, so their percentage of permeability, and they needed that data to figure out where a suitable area for a pond would be. So why do they use FME for this process? So based on the large amount of data and the data types that I'd be working with, I needed a piece of software that was quite dynamic and in the development process, so I could easily change and adapt it depending on what the requirements were from the water team. And the large range of transformers that FME offers allows me to manipulate the data to a form that fits the needs of the objective. So we'll quickly talk about the method here. So the input data we were working with was a culvert network data. So that's where all the storm collection data it flows into. And this was for Derry City. And this was developed by using a mixture of NI Water's data, as well as our water engineers as well had also developed this data so that it was complete network. We had the sewer network data and the outfall locations for the entirety of Northern Ireland produced by NI Water. And then we had a extent for the city. Again, the remote sensing data was also used as well, which this included the catchment volumes and their permeability rates. So here's a little basic workflow of what the entire workbench does. So we're taking the outfall, all the data, and once it has been basically clipped down to the city extents that I mentioned about earlier, the culvert network is used to identify where the what outfall locations that we're interested in. So the ones that connect to these culverts, and then based on that, we can also find the networks, so the surface sewer networks that are linked to these outfalls. Once we have those networks identified, we used a stream order calculator to help us identify where these main runs were within the networks. Based on that, we were able to then produce a ranking system where we could rank each run based on their topology. And using both this data, we were able to concatenate it together to create a unique ID for every single individual run. Again, at the very, very end, once this was done, we incorporated the catchment area data that was collected from the remote sensing as well, so to produce the final output, which we'll talk about in a bit later on. So this is the entire workbench, which is it's quite hefty, and you can probably tell I'm a bit of a fan of the dark theme as well. I do love the dark theme. It makes everything look more sciencey, in my opinion. But based on just how big the workbench is, I'm just going to focus on three key areas, which is the stream order power generation, the ranking runs within networks, and the unique ID generation as well. So we'll have a look at the stream order powers first of all. So this stream order calculations are used quite a lot for looking at river catchments and looking at river networks. So giving like a hierarchical sort of ranking to catch or connections within a river network as they go from the source down to the mouth of the river, for example. So we thought we could incorporate this into essentially the collection network, because it's doing the same thing. It's collecting it from the tributaries and then distributing it down to the culverts. So using the culvert, or sorry, using the outfalls that are connected to the culverts, we use that as essentially the mouth of the network. And we took the surface collection network and ran it through a Horton stream order calculator. So that was one of the sort of calculations we could use for stream order. And that allowed us to then produce a visualized representation of this network data that identified where the main runs were, where everything fed into in this network. So you can see on the right-hand side there, I've done a crude little kind of visualization of what the data kind of looks like, but it's essential. You have a central run and then smaller tributaries connecting off, and they have diminishing powers depending on how many connections they have. Another little aspect that we did as well was to make sure that there was no two areas of the same power connecting, because this needed to be, this is important for a later stage when it came to ranking things. So there was a process where I helped or identified where this two powers connected, which were the same, and then use a process based on the diameter of the network pipes to apply a sub-power to that. So this is the small area here of the workbench that does all that. So we can break it down into the Horton stream order calculations, and then there's a section where I've identified where the two runs of power intersect, and then apply the sub-power to those based on which one was the smaller diameter pipe. So once we have that data, we are then looking to trying to create a ranking system for every single individual run. So how we did this was by generating a connection node at every single intersection. We measured the point of where those nodes were across each power run. So, and then based on that, we could rank their measurements. And then this is taking into account direction of flow as well. So making sure that it's flowing away from the source, away from the outfall location. This allowed us to basically have a unique ID of every single connection point along a run, so that we could identify which junction it was along each individual run. And this data was very, very important for the generation of the ID later on. So again, this is split up by power. So we're looking at every single individual power run. We are then counting which intersections are along that run and then ranking them based on their position. So once we have that data, we have both the surface collection network that has their Horton orders as well as their ranks. We were able to create an ID on this. And this was done by using a distance finder, because we were trying to locate what path a run was taking from its position or its central node towards the outfall location. Based on that, we used a shortest distance finder to generate that route and list up all of the other sort of runs that were involved in that journey. From that, we were able to explode that list and then rank them based on their order. And because none of them had any duplicate orders, they were all ranked in the correct order based on that. So that was where that other work came in earlier, where we made sure that there was no two orders the same that were connected to each other. This then allowed us to then concatenate these together to create a ID, which was essentially a path that this flow takes from a selected node in the network. And so this is how it's broken down. So there's just it generates the midpoints of the runs, creates a vertex, which we then used for the shortest distance finder, and then we created a list which had all that data, exploded it, and then aggregated that together. So the final output looks something like this, which is, I know all the technical parts are a bit boring, but the outputs are quite fun. So we have on the left-hand side there the visualization of the network for Derry. Now, if we ignore the dark blue, that's the actual culvert network itself, you can see that there is varying colors on the other network connected to it based on their power. You can quite clearly see that there are some dark red lines which indicate the main runs within that network. And that allows very, very easy visualization of where those are, whereas beforehand, the water engineers would have to go through and try and manually find them based on a number of different attributes. So if we take our eyes more to the right-hand side there, we can see that the ID there shows what culvert it's connected to, as well as all the different rankings that have been concatenated together. And every single one of those IDs are unique, and there are no duplicates. Any sort of duplicates were based on topography errors, and we were able to, or topology errors, and we were able to go back and fix them. So the data also presents the Horton order, and then the last four rows or columns there show the catchment data that I talked about earlier. So based on a spatial relationship, we were able to identify which runs occurred in which catchments, and then we were able to apply the associated data based on that. So we took this and went back to the water team and did a bit of an assessment with some of the water engineers there, and to check the accuracy of it. And we were getting over 90% accuracy in terms of identifying where main runs were and producing data that they would have done manually. We also tested this actual workbench for the entirety of Northern Ireland just to see what would happen, and it was quite an impressive outcome actually. So there are potential further developments for this workbench to be used on other projects in Belfast. We are also taking this data and producing a web viewer for it so that we can produce other sort of visualizations. There is something in the work that is a family tree currently, where it takes, if I go back, takes the ID data and creates a hierarchical family tree that collapses into each other. So you can take the spaghetti junction of networks there and create an organized sort of a network and a family tree sort of representation, so that people can understand what junctions connect to where and the sort of catchment data that's associated with that as well. So yeah, again, I'm sorry I couldn't really go into too much detail about the stuff, but I'm happy to answer any questions that are asked. So yeah, back to you, David.
Thank you, Declan. That's really neat to see. I quite like the family tree idea, the ability to sort of collapse things. It's sort of visualization of the nesting is really interesting. There's a couple of questions. There's one is specifically about the Horton stream order calculation. The question is whether you used a custom transformer for that, if you called some Python that somebody had already put together in the open source community, or whether you sort of strung together a series of standard transformers. How did you do that that part of the process?
So the stream order calculation, there's actually a transformer which is dedicated to generating that. So you can, the selection I believe is between Strathler and Horton within that transformer itself. The data that we used for it was all based on what we had from the NI water data set. So the requirements are a network after we've generated the topology, and a like an outfall location, or the mouth location for the generation. So we had that as the outfall data. So there wasn't much custom work went on. Everything was out of the box when it came to FME. So yeah, it was fairly standard stuff, but it was very, very useful either way.
Okay. You don't happen to remember the name of the transformer, do you? I actually, I'm not familiar with. It's presumably a parameter within an existing tool
For the stream order calculator,
for the stream order calculation. Yeah.
I think it was called stream order calculator.
Oh, okay. Okay, fine.
I obviously can double check that. It's hard to see in those images because they are so
Yeah,
zoomed
no,
out.
that's
But
fine. That's fine. I'll look that up in a moment. The other one is more about your sort of start with FME. Do you have any tips for a new user in getting up and running quickly with FME based on your experience? It sounds like you were thrown in a little bit to this project.
I think in terms of my understanding of FME, and it's definitely growing. And I did initially go on the basic training course. So that was but I did that after maybe a month or two of already playing around with FME. So that definitely helped solidify a lot of the foundation of understanding that I had just from playing around myself. But actually going on and looking through and reading what each of the transformers does as well is quite important. So looking online, there's a lot of tutorials as well. So if you type in what you're trying to achieve, or even from my case, because I have a background working a lot with Esri products, I know the name of stuff that I want to do in ArcGIS, for example. I could then type in what is the equivalent. Yeah, that's the calculator. That's the one there.
There you go. You were
There,
right.
I could type in basically what is the equivalent in FME, and then there is a lot of help online, a lot of forums, where you can post questions as well. So yeah, I think the majority of my initial knowledge came around from just playing around with stuff. Obviously, I had the support from my team members as well, which also helped. And then the official courses as well was also an influence too. So yeah, it's a
Okay.
multifactorial sort of influence there.
Yeah, no, I mean, there's a couple of things you mentioned there that we advocate as well. So it's good to hear that. I mean, the knowledge center that you can use to ask questions on, or just go and browse, is an incredible resource actually, and there's a lot of extremely helpful and enthusiastic people who will dive in and answer your questions. The trick is to form a question properly so that people have got a chance to answer it. So that's really good. And from a training point of view, actually spending a bit of time using the software before you go on some formal training is really important, because the benefit of that then is you've got some baggage to bring to the course with you to try and unpack. So yeah, that's nice to hear as well. So fab. Thank you very much. Really appreciate you joining us, Declan. Cheers.
No worries.